Okay, this is section 12.2. We are going to go over ellipses, and I don't think we're going to do another implicit differentiation question because you just did that in 12.1. But we are going to go over ellipses. So an ellipse is another conic section, and the definition technically of an ellipse is that it's all points, the sum of whose distances from two distinct fixed points, which are the foci, is constant, but you don't have to know that. So down here I have two ellipses shown, and the foci would be somewhat, it'll be along the what's called the major axis, the longer diameter, if you will, and the middle of that major axis is the center, and the foci are going to be at 2 points in between, 2 points along that axis. This was the major axis. And then the minor axis is the other diameter, the shorter diameter, if you will. And I know I'm saying diameter here, but this is not a circle. However, it's really convenient to think of an ellipse as a confused circle, or a circle that has two radii. So one radius is the major axis radius, and it is the distance from the center along to the longer. It's called a vertice. So the vertices, which is plural of vertex, are along the major axis, and the co-vertices, I think that's a term that we use for ellipses, but I don't believe that our book mentions that. The co-vertices are the vertices along the minor axis. Okay, so these are some important points to know for an ellipse. There we go. Okay, so the most important thing for an ellipse are two different things. The same thing as with a parabola, which is the connection between the graph and the equation in standard form. And so if you know the equation in standard form, you know everything about the ellipse. And if you know the graph, then you know the equation in standard form, and vice versa. So that's what we work with. We work with the graph and the equation in standard form. Okay, so here is our standard equation. The book does something extremely confusing, and actually all books do this. It's very confusing, and I refuse to do it. The book gives you two different formulas, one with a under x and one with a under y, and they just make a the bigger one, and I think that's ridiculous. So we don't do that. A is the x radius, and this is a Mrs. Griffith term. It doesn't really exist, but it works out. It all works out nicely if you think of it that way. And B is the y radius. And HK is, again, your center. Just like in a parabola, the vertex is HK. In all of these conic sections, we're going to use HK for the central point. Okay, so we have center HK, x radius A, y radius B. Your vertices or co-vertices, you do not have to write this down, but essentially what's happening here is that you'll have your center, say right here, H comma K, and so you'll decide, okay, my y radius is B, so I'll go up B and I'll go down B, and that will be my two either vertices or co-vertices. It depends on whether B is the big one or the small one, but it doesn't matter which one it is. And then A is your x radius, or the number under the thing that's squared with x is your x radius. And so you'll go left and right that amount from the center, and then boom, here you go. There's your ellipse. Okay? Now, to figure out the foci, this is the reason why books change things around, why they give A. They always make A the bigger one so that it's easier to find the foci. But I think that formula is silly. So what you do is this strange version of the Pythagorean theorem, where you have a minus instead of a plus. And if you're doing a minus instead of a plus, then you just have to do the bigger one first. Okay? Just whatever the bigger one is, c squared equals bigger one squared minus smaller one squared, whichever one it is. Then once you get c, the foci will be c away from the center, but on the bigger axis, whichever one it is. Okay? That's right. The other thing that we study with the ellipse is something called the eccentricity of the ellipse. And the eccentricity of the ellipse literally is just a measurement of its um, likeness to a circle versus its or its likeness to an oval. Its squishiness of the circle, how oblong it is. There you go. So the eccentricity of the ellipse is the measurement of how oblong it is. The way you measure it, or the way that you calculate the eccentricity, is it is the focus radius over the major axis radius. Okay, major axis radius, semi-major axis radius, same words, same meaning. It means the same thing. Okay, so here we have an example, and what I've given you is the equation of an ellipse in standard form. And then we're going to do another example in which it's an ellipse, but it's not in standard form, which means we'll have to complete the square. So here I have the equation in standard form. And remember, the highlights of standard form are that you're going to have an x squared, a y squared, a plus between them, and equals the number 1. It has to equal the number 1. Okay? Now, the rest of the details tell you information on how to graph the ellipse. So let's start with the graph. And again, I work with this just the way I work with parabolas. I work with the graph to do it, and then just read it off. So the center is going to be HK, and that will be -1, comma 0, because y doesn't have anything added to it, which is right here. My x radius is the square root of the number under the x part that was squared. So that's a nice pretty 3. So out from my center in the x direction, which would be left and right, I go 3.3 3 ticks, and I put in my vertices or covertices, whichever ones they are. And then the y radius is what's under the square root of what's under the y. So that would be 4. So now I'll go up 4 and down 4. And so now I do know which ones are the vertices, because 4 is bigger than 3. This is actually oblong vertically, not horizontally, even though I'm a little off there. So here's the picture of my ellipse, and here's the major axis vertically. All right, so the next thing to do would be to find C, where the foci are. And to do that, I'm going to use that strange version of the quadratic, or the Pythagorean theorem, in which c squared equals a squared minus b squared, or bigger squared minus smaller squared. So that would be 16 minus 9 here. And 16 minus 9 is 7. So c is the square root of 7. I have no clue what the square root of 7 is. Well, wait, I do know. It's between what? 2 and 3. Because it's between the square root of 4 and the square root of 9. So I'm going to go somewhere between 2 and 3. This distance is square root of 7. Up and down. And those are my foci, or F for foci. And so what are the coordinate points of the foci? So you can just kind of figure it out from here. The x-coordinate would be -1 for both of them. And then the y-coordinate is going to be the y-coordinate of the center plus square root of 7 to get to the top one, and minus square root of 7 to get to the bottom one. And so you can list both of them in one by just saying plus or minus the square root of 7, or whatever your C was. That will work. Okay, so I found the foci, I have the graph, I have the center. Let's find the vertices. The vertices are the ones along the major axis. I'm going to list those down here. And so that's when x is -1 also, but my y values were 4 and -4. Let's just list them in one again, plus and minus 4. And eccentricity. So the eccentricity, E, was C over the bigger one, right? And so in this case, C is square root of 7, and the larger one was 4. So the eccentricity is square root of 7 over 4. And that's all the information they requested. Okay, and so here I have a second example asking for the same things. The only problem is that the equation is not in standard form. And so our first task is to put it in standard form, which means that we get to complete the square twice. So to complete the square twice, I'm going to first gather my x's together. And then I want to okay, so I'm not going to complete the square quite yet. Plus, and then I'm going to gather my y's together and put my constant 16 on the other side, okay? The next thing to do is when I complete the square, I really, really hate a number in front of the squared part, and so I factor that out. So I'm going to factor those out. So this is 16x squared minus 2x, and then I'm going to complete the square inside of this parenthesis. Same thing with the y's. I'm going to factor 25 out and complete the square inside of the parentheses. It just makes it much nicer. Now, so when I complete the square, you add the magic number to each side. And the magic number inside of this parenthesis, the magic number is b over 2 squared. And so here, 2 over 2 squared is 1. Well, 2 over 2 is 1, and 1 squared is 1. Same thing here. Now, whatever you add to one side of the equation, you also add to the other side of the equation. And this is where we get tricky, because now you have to think, what did I add to this side of the equals? What did I add to the left side of the equals? Well, I added a number 1, but I added it inside of a parenthesis. And that the things inside of that parenthesis are being multiplied by 16. And so truly, I added 16 to the left side of the equation when I completed the square on the x. And when I completed the square on the y, even though it looks like I added 1, I really added 25 times 1, and so I'll add 25 to the right side since I added it to the left side of the equals. Okay, and that's the hardest, trickiest part here. Now, well, yeah. Now I'm going to complete my square. This will completely factor as x minus 1 quantity squared. And then on the right, or with the y, I have y plus 1 quantity squared. The difference being that the b's were negative and positive there. And then on the right side, I have the number 25. So I'm not yet in standard form. I'm doing much better, though, because my x's and y's, you can see what h and k are already. The problem is that this side of the equation must be the number 1, okay? And I don't want a minus 25 or minus 24, because if I minus 24, I would mess up the left side of the equation. So the other way to turn this 25 into a 1 is to divide by 25. And so I'm going to divide each side of the equation by 25, and I get the desired equals 1 result on the right. And then I'm going to distribute this divided by 25. And so on the left side, I have x minus 1 squared, and this doesn't reduce. So it's a 16 and 25 here. But then on this y, the 25's canceled. So that's just over 1. All right, and then I'm going to do some trickery because it's still not in standard form. This 16 is not okay. He is not okay. But you can do something silly. Oops. And you can divide the top and the bottom by 16. It's like multiplying by a really weird version of 1. The one version of 1 being 1 over 16 over 1 over 16. Okay, and so this is in standard form. It's not the easiest of examples. The numbers aren't quite that pretty, but it still works. And so let's answer some questions here. What is my center? We've known this for a while. The center is 1, negative 1. What is the x radius? Well, the x radius will be the square root of 25/16. That's 5/4. So just 1 1/4. The y radius is going to be 1. Okay, and let me sketch a graph. 1, negative 1, x radius 1 1/4, y radius 1. And so you can see I have a horizontal ellipse here because the x radius is longer than the y radius. So let's go ahead and say the vertices. So the vertices are, well, the y-coordinate stays the same. The y-coordinate is -1 no matter what. But the x-coordinate, it's going to be the center back the x radius and then the center right the x radius. So that would be 1 plus or minus 5/4. Those 2 points there. Okay, and then let's find the foci. To find the foci, I have to find c. Remember, c squared equals a squared minus b squared, or whichever one is bigger minus smaller one. So c squared here is 25/16 minus 1, which is 29/16. And so c is 3/4. So once I know c is 3/4, then I know the foci are 1 plus or minus 3/4, -1, because they're also along this major axis or semi-major axis. And finally, what's the eccentricity? That would be c divided by the bigger one. So 3/4 divided by 5/4, or 3/5. And I think that's all that this question asks. All right, in our final example, we're going to be finding the standard equation, and so we don't know the equation this time. So the way that we work this, or the way that I find it's easiest to work it, is to start with the picture. So the foci are at plus and minus 2, 0. So that's along the x-axis. Just knowing the foci, I now know the center. Where does the center of this have to be? Well, the center is exactly in between where the foci are. So I know that HK is 0, 0. Okay, the other thing that I've been told is that the major axis has length 10. So I know the foci lie along the major axis. So if this is my major axis, then the length of it is 10, which leaves me 5 for either side, which tells me that my x radius is 5. Okay, so I'm doing pretty good. Let's write down what the standard equation for an ellipse is. Okay, so I already know h and k are 0, 0, so x squared, y squared. And I've been told that the major axis is horizontal, and the x, so that means it's an x radius, and that the x radius is 5. So I have to put a 5 squared underneath the x squared. So the only thing left is what in the world is b. So how can I figure out what b is? Well, the way I figure out b is I know c. Because the foci are plus and minus 2, 0, then I know that this distance c, this distance c is 2. And so if c squared equals a squared minus b squared, or bigger one minus smaller one, then 4, or 2 squared, is 25 minus b squared, and b squared is my y radius. I don't even have to square root because I want to know exactly what b squared is. So if I subtract 25, I get -21. So -21 is -b squared, so b squared is 21. And so I just need to put a 21 under there, and we'll be finished. So x squared over 25 plus y squared over 21 equals 1. All done. And that's it.